Hi, so I'm Amy Milne, a first year PhD student at Imperial College, and today I'm going to present my work on the uniaxial compression properties of LPBF 316L stainless steel. So here's a quick outline. I'll start with describing the process, talk about the project motivations, and then go through my method and results. So the samples that I made were built on a Renishaw AM250, as you can see there, and in the process, a layer of powder is spread across the build platform. The laser then fuses the first layer and the roller spreads a new layer, and the process repeats until the part is built successively layer by layer. So for my samples, we used a stripe scanning strategy with a rotation angle of 67. You can see the rest of the build parameters on the side of the screen. The build direction was also parallel to the applied force during a test. And you can see what I mean by that from the picture up there. You can see the stripes going upwards and the force is being applied downwards in the compression test. So it's the same build direction. At the minute, laser powder bed fusion parts may contain high residual stresses, porosity, and anisotropy, which can be caused by the variations in the microstructure. The mechanical properties have also been shown to differ quite significantly from raw material and show a lot more scatter. So these are the samples that I tested in compression, and I want to be able to quantify and compare the compressive response of 316L. So I'll do that by comparing the compressive and tensile response to the material, and then I'll compare the tensile response of it to its raw counterpart too. So I started off by doing some microstructural analysis on the untested samples, and this was sliced vertically down that way. And no crystallographic texture was observed, and so there was no preferential orientation of the grains. You can see several elliptical pores on here, about 70 micrometers in length, and they're elongated along the build layer. So in compression, these are likely to be closed, but in tension, there's a chance that these can create a large stress concentration factor and reduce the performance of the part. So for the compression tests, you can see my setup here. I first placed the sample between two Inconel plates on the side, and then between the compression plates. Used a 200 kilonewton load cell to preload it to 2 kilonewtons, and then heated it up to temperatures from between 20 degrees, which was room temperature, and 700 degrees was the highest test. There was ceramic wool used at the top and the bottom to prevent any heat escaping and keep a constant temperature gradient. And the lamps were used to illuminate the sample so that I could use the camera to take pictures at 5-second intervals and monitor the axial and radial deformation throughout the test. The fans are pointing in front of the camera lens to remove the effect of heat haze, and I also had a thermocouple attached to the top and bottom plate to make sure that the temperature gradient was stable. A powdered graphite lubricant was also used on the top and bottom of the sample to prevent any barreling and make sure I got reliable results. The ASTM E9 standard was followed for the room temperature test, and then E209 for high temperature. So as I mentioned, I had two methods of monitoring displacement during the test. We started with machine displacement, which is directly extracted from the machine and then processed into true stress, true plastic strain data, and then edge analysis from the camera. So it was really important to focus on the edge of the sample and then put it through a MATLAB code, which detects the increase in diameter and the axial radial deformation from the images. I think I forgot to mention as well, it was a quasi-static test, so it took about 40 minutes to complete and enter complete linear hardening. So these are results from the compression tests, and you can see that as expected, the compressive strength decreases with temperature as temperature increases. The compressive yield strengths are also much higher than all of the tensile yield strengths, with the exception of 200, which didn't have a tensile yield strength result for. And these were all taken at 0.2% plastic strain. So yeah, as I just said, the compressive yield strength of 570 megapascals is much higher than that found for tensile strength at room temperature, and the difference is likely due to non-isotropic hardening mechanisms, which I'll talk about in the coming slides. Again, compressive strength decreasing with temperature increasing because you've got the activation of dislocation motion, allowing for more plastic deformation. So jumping to the wrought material, this is LPBF 316L being compared to wrought 316L, and you can see that there's a higher tensile strength for the LPBF material, likely due to the small grain size and the high dislocation density from the successive welds and the fast cooling rates, which give you incredibly small grains. And now I'm going to compare both laser powder bed fusion, tension and compression samples. So you can see in most of these on both slides, the compressive yield strength is higher than the tensile yield strength, with the exception of 200, which came from a tensile model, which we think is quite unreliable for the early plastic strains. But for the rest of them, it does line up with the expectation that the material will perform better in compression. You can also see that the curves begin to deviate further apart at higher temperatures. And the reason for this could potentially be due to some stress relaxation occurring, because the samples were held at temperature for an hour before the test occurred. So at 700 degrees, is it on here? It's had time to relax. There's more potential for hardening to occur. So the reason for this, you've got the compressive strength exceeding the tensile strength for all temperatures, and this is likely due to back stresses formed during the build process. Because the scanning strategy affects the thermal gradient and it creates a back stress, which resists the forward motion of dislocations but allows them to slide back inside grains. So you've got an element of kinematic hardening present, which is accounting for the difference between tensile and compressive strengths. So yeah, the back stresses exist in these materials with this microstructure, and they represent a significant portion of the high tensile and compressive strengths. This agrees with some other work which found that the back stress was equal to the difference between the wrought yield strength and AM yield strength. I then looked at the hardening rates, and I plotted the normalized hardening rate against the true strain corresponding to different temperatures. Again, these results agree with literature. And as I mentioned before, the samples were held at high temperatures prior to testing. They likely underwent some relaxation, and so their strain hardening capability would have increased. Although you can see it's quite similar for a lot of the mid-range temperatures there. So going back to the optical analysis that I was performing at the same time. So the edge of the sample was tracked using the Nikon D7000 interval timer shooting setting every 5 seconds from the start to the end of the test, which lasted approximately 40 minutes for each sample. I did find good agreement between the optical results and the machine displacements. This is really useful for the future because it's not always possible to use things like capacitance gauges inside tests. So it's good to know that the optical method can provide a way of monitoring the sample in real time and getting those axial and radial displacement results without externally from the furnace. So yeah, just in summary, the compressive and tensile strengths decrease with temperature as we expected, and the compressive strength of 316L exceeded its tensile strength at all temperatures, likely due to the kinematic hardening present alongside the isotropic element. The tensile strength of powder bed fusion 316L exceeded that of the raw due to the small grain size and high dislocation density, and the optical method closely matched the machine measurements at all temperatures, which means it's suitable for use at high temperatures where other gauges can't be relied upon due to their limitations. Thank you.